Okay, there's just a couple of things I just wanted to mention about pressure and barometers that we just didn't get time to talk about in the previous video. Okay, so first up, remember when we were talking about the barometers and everything, we were saying that these were referenced relative to vacuum. Now, if you're actually dealing with things like these little tire gauges and such, these aren't actually referenced to vacuum when you're putting the pressure in your tire. These are referenced to the outside atmospheric pressure. So if you're pumping your tire up to, let's say 5 atmospheres, in reality it would be 6 atmospheres relative to vacuum, but 5 atmospheres relative to the outside pressure. And that's, of course, if you are pumping up a ball or a tire, you want to basically have the same firmness, basically the same balance between the outside and inside forces. You're not really caring about the absolute pressure. All you're caring about is basically like the stiffness of the wheel or the ball. So that's why these things are referenced relative to atmospheric pressure. So the actual pressure could be different if you're in Mankato or Denver. So one of the aspects to pressure, and something that everyone has done at one point or another, is try to drink through a straw. And it's one of those things that, if you really don't think about it, it's just so natural. But again, it's a natural consequence of pressure, and also, if you think about it, why barometers actually work here. So I will do a very bad drawing of someone drinking through a straw. All right, so there's my very, very bad drawing. Now, of course, what's happening in here, this blue liquid here, is, of course, your water or whatever else you're drinking. And this is, of course, going up the straw into the person's mouth, right? So when this is happening, of course, the whole reason that the straw actually works is that we have over here, the atmospheric pressure pushing down, and inside your mouth, you're creating a slight vacuum. So, inside your mouth here, the pressure in the mouth is going to be just slightly less than the pressure of the atmosphere, okay? And that's why the liquid goes up, because the same way in which we had the vacuum here, where we had, essentially zero pressure, well, then that sucked the mercury up because the mercury was being pushed down here by the atmosphere to go up this way. So the same way we have over here, the liquid is again being pushed up because of the atmospheric pressure pushing the water down into there. And of course, if you were to create, the mouth pressure be larger than the atmospheric pressure, well, that's when you, of course, blow bubbles in your water or your milk, and your parents tell you to stop that, right? So that's essentially, what's going on when you're sucking with a straw. You're just creating a miniature vacuum. Now, if you remember what we talked about last time, remember we said here that from the whole density of water and everything, that 10 meters of water will be equal to 1 atmosphere of pressure. Now, of course, if we just have 1 atmosphere of pressure pushing down on here, that basically gives us a maximum length that our straw can actually be. So essentially, you can't drink water from a straw longer than 10 meters. So if you're more than 10 meters away, and what I'm saying 10 meters above, it's not going to be 10 meters, horizontal. This is basically from this point up to this point. This is what we're measuring, the height of the liquid to the location of your mouth. So from the liquid top to your mouth cannot be more than 10 meters. If it is, you cannot create enough pressure, no matter how hard you try, to actually suck the water up, because there's not enough atmospheric pressure pushing down, and the weight of the water will prevent it from going any further up. Now, in reality, if you actually do try this, there's actually more like a practical limit. So practically, you can't really drink from a straw more than 7 meters high, because, of course, if you're a person, you cannot actually produce vacuum in your mouth, so that's going to limit it. And also because water has a fairly high vapor pressure, that will also limit how high the water can actually be sucked up. Now, as I mentioned in the previous video on this, we talked about that, yes, trees, they use capillary action, where the water molecules can literally just climb up there. But if we're dealing with, a macroscopic size straw, then the capillary action is minimized for that. Now, also, as part of this sucking, we can also look here at what happens with a hurricane. So what we'll basically draw is like a little cross-section of the hurricane here. Basically in this middle portion, here's the eye of the hurricane. And then, it just goes off, as the winds will come off like so, right? So that's the minimum portion. The eye is where, of course, the minimum pressure of the hurricane actually is. And then, of course, you have all the storms and everything rotating around there. Now, what actually happens is the water. That's, of course, the hurricane's on the ocean. So what happens to the water level is that it actually goes something along these lines here. So out here we have about 1 atmosphere, about 30 inches of mercury. And this is, of course, when you're far away from the center of the hurricane. When you're in the middle of the hurricane, well, that's going to be, your central pressure. And if you remember from Hurricane Wilma, that was 882 millibars, which we calculated out to be about 26 inches of mercury, or 0.87 atmospheres. So over here, the pressure is going to be less, or about 26 inches of mercury. So, of course, just like the person sucking through the straw, my water over here is going to be sucked upwards in the middle of the hurricane. So on the outside of the hurricane, where the pressure is basically normalized, this is pushing down. In the middle, we have a lower pressure, so the water is literally being sucked up because of this low pressure, just like the person, drinking with a straw. Now, how much is this sucked up? Well, with the Hurricane Wilma, which was at this particular pressure, we noticed that there was about a 4-inch of mercury difference between them. Also, remember what we talked about last time was basically, the density of mercury is 13.6 times that of water. So if the mercury decreases over here by 4 inches, the water is going to be 13.6 times greater than that. So therefore, 4 inches of mercury is basically going to be 13.6 inches of water for every inch of mercury. So basically, for every inch of mercury, the water is going to go up 13.6 inches, so a little over a foot. And of course, if we work this out, this is going to work out to be about 54 inches of water. So that means that the height difference between the outside of the hurricane and the center of the hurricane is going to be around 54 inches high. And that's just, the water has been sucked up by 54 inches, and that's, quite a bit. And you've heard about the dangers of storm surge and hurricanes, and this is part of the reason that, hurricanes have large storm surges. We have, of course, the water is literally being sucked up because of the lower pressure, and that, of course, raises the ocean level. And as it goes on shore, this water will, of course, come along for the ride. This is just part of the reason that hurricanes have storm surge. The other part is, of course, all the gigantic amounts of wind that actually helps push the water. So it's really two competing factors. You have one is, the lower pressure sucks the water up, and the secondary effect, of course, is that you have all the wind blowing the water onshore as well. So this is, something that's, usually not really thought about, but, again, is another application of, pressure differences and everything. All right, another thing, you will also see the pressure related to is, of course, the weather. So if, as you know, if we're dealing here, with, here's, let's say, here's the ground, and, up here is, of course, space. Well, the pressure as a function of altitude is going to decrease, because down here you're going to have, a lot of pressure because you have all the weight of the atmosphere above you. But then as you go up, it's going to slowly decrease and get smaller and smaller because, there is less air above you, like this. All right, and actually here's just a little graph just kind of showing the relation between atmospheric pressure and altitude. It's an exponential relationship, and it's a bit more complicated than we want to go through and try to derive here. But basically, this is what it kind of looks like. Now, of course, if we're looking at, our pressure, that of course means that, if you happen to be living up here on a mountain or something, the pressure on the top of the mountain is going to be lower than the pressure at sea level. So when you report pressures, for your weather, they always correct these things to sea level pressure. So if you're close to sea level, it's a fairly small correction, but of course if you're at a very high altitude, like living in the mountains, this can actually be a pretty big one. So if you're in Denver, which is about a mile above sea level, the correction factor is quite significant, but for Mankato, it works out to about 3%. Okay. So Mankato is about 300 meters above sea level. Of course, that depends a lot where you are actually in town. But this is actually going to be about a 3% correction. So actually, the pressure that we experience here is actually about 3% lower than the pressure that they would actually report, on the news, or if you even just look up, the pressure in Mankato, because they always correct these things to sea level. And the reason they do this is, if you think about it, really what matters more is, what is the pressure up there in the clouds, and you just want like basically a nice uniform base that you're actually referencing. And if you didn't do that, you would kind of be looking, there would be like permanent low pressures kind of hanging over the mountain regions, and we obviously just don't want that. And of course, if we are dealing with pressure in the atmosphere, the whole reason that we have wind is because of pressure differences, right? So if we have, an area of high pressure and an area of low pressure, the wind will try to equalize out those different pressures. And that's why, of course, we have wind. And the reason that we have high pressures and low pressures is because the Earth is unevenly heated. You know, the sun is obviously shining down. It has different amounts of energy that's delivered at the equator versus the poles. So we have, you know, warmer air there, cooler air at the poles, and also we have oceans and land. The ocean doesn't warm up as fast as the land does. Again, you know, this causes areas of high pressure and low pressure, and this can cause, you know, breezes to come in off the ocean or from the land, depending on the time of day here. Really, all of this, you know, is basically all of our weather is driven by pressure differences. Okay, then finally, we'll just start discussing about blood pressure. Of course, I'm writing this in red because we're dealing with blood. So the first thing is our bodies are going to be at slightly greater pressure than the atmosphere. And this is actually very important and kind of obvious when you just stop to think about it, because of course if you poke yourself, and I'm not going to do it here because it will cause some students to probably faint on me, but if you poke yourself, of course you bleed out, right? So that's of course meaning that, you know, there's a higher pressure inside, which is forcing the blood to come out. But if there was a lower pressure inside of you, well, then that would mean that air would be starting to be sucked in, which would be bad. All right, so of course, you know, we need this higher pressure on the inside to actually force the blood out. So that's why we're actually, you know, slightly pressurized relative to the outside world. All right, and the thing which measures the blood pressure is called a sphygmomanometer, and hopefully I pronounced that correctly. And this is just, you know, your blood pressure meter. So probably all of you have done that. You know, they put the little cuff around your upper arm, they pump it up, pump it up, pump it up, and then, you know, they slowly release the pressure, and, you know, from there they can determine your systolic and diastolic pressures, right? Common values you may see from these, and, you know, if you're in good health, is probably like 120/80. And the units on this is actually going to be millimeters of mercury. All right, so what they're actually reading is the pressure that your body is above atmospheric pressure, and the typical values are going to be, you know, 120 to 80 millimeters of mercury. Again, remember, 1 atmosphere is 760 millimeters of mercury, so we're just, again, slightly, you know, about 10-20% or so above atmospheric pressure there. Now, how do they actually read the blood pressure? All right, so again, remember they put, you know, the cuff on you, and what they're really reading here is basically the maximum and minimum pressures that your body is actually putting out, because of course if you are alive, you hopefully have your blood pumping because you have a heart, and when you're reading this, essentially what's going on here, so if I just draw a little graph, so this would be time, and then this would be your pressure. All right, so that's the pressure, that's time. And essentially down here would be like your 80, up here would be your 120. And what's going on is that, you know, as your heart is pumping, you know, at the low point, you know, it's going to start down here. Then of course your heart, you know, gives that little squeeze that gets the blood moving. So then it comes up to here, and then it reaches its maximum value, and then it starts decreasing again. And then it goes up and down and up and down and up and down and up and down, right? So that's your pulse, basically how the blood is actually moving through you. Now, it's probably not as nice and sinusoidal as this, but, you know, you get the idea there. So of course when they're doing this, and let's just say this is my arm, you know, where your artery is, and they'll just, you know, wrap the cuff around the upper arm like so, and then, you know, what they do is they squeeze really, really hard, and essentially what they're doing is they're applying more pressure to the outside than your heart is currently pumping. So then you're essentially starting up, you know, at this very high mark over here. All right, so this is like that little cuff that they have around the arm. So when they have this high pressure, and then what they'll notice is that if they've watched the pressure reading, remember they always have that little dial, and that's basically just a little mini barometer that they're actually reading, you know, the pressure from inside the cuff. So if they're above there, no blood is actually getting from your upper arm into your lower arm, and because of that, you know, they won't see any little jumps in the dial. So basically they're looking for a little jump kind of like this, you know, as your heart is beating. So that's what they're looking for, little jumps in the dial. If they don't see any more jumps anymore, they know that they have applied more pressure than the heart can supply, and that's going to be more than your maximum pressure. And then of course what they do is they slowly release the air coming out of there. So now your pressure in the cuff is going to slowly start dropping, and it's going to keep on going down, 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 down until, you know, they reach this bottom value here. So this blue line right here, that's basically the pressure in the cuff. So as they slowly release it, eventually they get to this point. And now at this point, the heart can finally start flowing just a little bit of blood through that cuff. So there's going to be a little bit that gets through. And now what the nurse is going to see is that the thing is going to jump up just a little bit. And it's going to see it jump up, you know, as your heart is beating. All right, and so as it goes down through here, you're going to see the little jump, 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 jump. And then finally what happens is once they get to this low point, it's going to stop moving again, because now that's going to be your constant pressure that's always in your body. Okay, so that's essentially what they're using is they pump up your thing to very high pressure, and when they don't see it, they're like, okay, I can start releasing the pressure in the cuff. They start releasing it. When they start seeing little jumps, that's going to be your systolic pressure. So that's going to be your high pressure in your body. And then they keep lowering the pressure down, 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 down until they finally get to where it stops jumping again, which is the 80, which is going to be your diastolic pressure. And then of course they report that, and then if you're too high or too low, they might give you appropriate drugs, tell you to clean up your lifestyle, and whatever else you need to do there. Okay, so that's basically what's going on with the heart. And I mean, if you kind of think about it, remember we had up here that pressure differences cause the wind, and our heart is essentially doing the same thing. It's causing little pressure variations that is pushing the blood along, and essentially it's analogous to the wind. It's just the flow of blood, the flow of air particles, same basic kind of stuff that's going on there. All right, and then just a few little things about different types of pressure meters. So there's also, besides the barometer and little gauges like this, there's also a few other types of pressure gauges that we'll talk about a little bit here. Many of you have had an aneroid barometer in your house growing up. These were the analog dial barometers. In this case, there is a sealed vacuum chamber which flexes slightly as the pressure changes. Through a series of levers, the small motion is amplified to move a dial. These aren't as accurate, but work pretty well for watching weather changes. Next we have the capacitance mammometer. Mammometer is just a more generalized pressure measuring instrument. These work from about 25,000 torr to 0.1 torr. A capacitor is an electrical device formed by separating two metal plates by an insulator. Capacitors hold charge. And when describing electronics, plumbing analogies are commonly used, and a capacitor is analogous to the toilet tank which holds the water for the flush. Anywho, the capacitance is inversely proportional to the distance between the plates. So to form this capacitance mammometer, two plates are separated by a vacuum. One plate is very rigid, and the other plate is a flexible diaphragm. So the more pressure, the more the diaphragm will flex, which changes the distance between the plates, and through some electronics, then the pressure can be determined. We can also put pressure sensors on silicon chips, and they have been added to smartphones and GPS devices over the past few years, and these are commonly used to get better altitude determinations or maybe even just monitor the weather. They work similar to capacitance mammometer in that they use a flexible membrane reference to vacuum. However, they don't measure the capacitance, they measure the change in resistance due to the strain of the membrane which is flexing. Technically, this is called piezo-resistive sensing elements, and they are made from doped silicon. The change in resistance is measured using a Wheatstone bridge configuration, and if you aren't into electronics, don't really worry about that. Next we have a thermocouple gauge, which operates between 10 torr and 10 to the minus 3 torr. They monitor how fast heat is conducted away by gas molecules. So when the gas molecules collide with the heating element, they will remove some of the heat, and then that is just measured by the thermocouple. Alright, and you have to be careful with these since the thermal conductivity of all gases is not the same, so something like air will conduct heat much better than helium. Next we have an ionization gauge, and this works best at low pressures. They operate best between about 10 to the minus 4th torr to 10 to the minus 9th torr, so about 100 microtorr to a nanotorr. But some can get down to 10 to the minus 11th or even 10 to the minus 12th torr, so that's a couple of picotorr. When we are talking about pressures this low, it might be more instructive to talk about the number density of gas molecules. I'll show this in the gas law example video later on, but using the ideal gas law, we can see that 10 to the minus 11 torr is equivalent to about 350,000 gas molecules per cubic centimeter. However, that is still much higher pressure than in interstellar space, which can be tens to thousands of atoms per cubic centimeter, and intergalactic space, which may have densities as low as a few hydrogen atoms per cubic meter. Alright, they are also very sensitive to gas composition, and they won't give an accurate pressure reading unless they're calibrated for a particular gas. A hot filament, basically like an incandescent light bulb, will emit electrons, and this is called thermionic emission. And then the electrons from that filament will then ionize the gas molecules, which will release further electrons. A wire collects the electrons and measures the current, and again, through some electronics, we can determine the pressure. And you don't want to use these at very high pressures because you'll burn out the hot filament and then it will be dead. Usually you'll have a thermocouple gauge on the system to prevent an oopsie moment when someone turns on the ionization gauge at too high of a pressure. Finally, we have residual gas analyzers, or RGAs. These are essentially mass spectrometers, and they detect which gases are floating about. The screen on the front ionizes the gas molecules which travel down the length of the device, which are then separated by mass, and then they are detected. Technically, this is called a quadrupole mass spectrometer. All right, well, there are a few others here, but these are the main ones, and that's all we'll worry about for now. So anyway, I will just stop this here.